Alrighty, we're going to go ahead and start going over 5.4. Now 5.4, never really understood why they do it in this order in this particular book. Stewart seems to think that it's a good idea to do anti-differentiation in 4.9, area by Riemann sum in 5.1, and then that bridge section in 5.2, and then on into the fundamental theorem of calculus in 5.3, and then he wants to go back to the indefinite integral. Now the indefinite integral is of course distinguished from the definite integral. When we were doing the fundamental theorem of calculus, and we were trying to find areas or whatnot, the definite integral actually has what are called limits of integration, okay? It is actually the integral from a to b of some particular function. The indefinite integral is, of course, without those limits of integration and is much more like an anti-differentiation problem. And so this one actually winds up being f of b minus f of a, right? This winds up being f of x plus c, right? You have to have that constant there. I think that this is basically just an excuse to practice our integration techniques. So we're just going to go ahead and do maybe one or two videos on this. I don't know, it depends on how far we get. I'm just going to go through a couple of examples just to I guess refresh or keep up to date our integration techniques. Now, if you have not received a sort of a table of integration techniques, you're going to need to get one of those. Just Google integration rules PDF or something like that, and about 15,000 of them will pop up. Because like I've said before, calculus teachers love sharing their stuff online. Now, this is x to the 3/2 plus 2x plus 1. Now remember, integration, just like differentiation, can be done term by term. So we can actually turn this into, and of course all constants can be pulled out in front, so that actually can turn into that. Now these two are relatively easy. The only one that's a little bit difficult is this one, and you just need to remember that despite the fact that there's a fractional exponent, the power rule is still undone in exactly the same way. So I need to add 1 to my exponent, so it becomes x to the 5/2, and then you put it over that new exponent. Same thing goes on here. This becomes x squared over 2, right? Add 1 to the existing exponent, which is an understood 1. And of course, this is a constant. This is 1, and of course, its integral is, or its antiderivative is x. You must remember the c, okay? And so this winds up being 2/5 x to the 5/2 plus x squared plus x plus c. That is the integral, okay? Now, I'm going to share a really corny joke with you in hopes that it helps you to remember to put the plus c. It's one of those jokes, one of those calculus jokes that I actually wish I could forget. But in the past, it actually has helped some people remember the plus c. And remember that if I have 1 over x dx, that is the natural log of x plus c, right? And so what I have here is, what if I have 1 over cabin d cabin? I have log cabin plus c. Houseboat, right? Houseboat. So I would basically, before I would hand out a cumulative quiz or something like that, I would remind all the student, don't forget about your houseboat, okay? Don't forget your houseboat, don't forget your houseboat, meaning the plus c, okay? So that was sort of code, and if that corny joke, I know it's really bad, and if you're really upset about it, you can blame Jessica's older brother Jay, because I'm pretty sure that he's the one that told me that joke. But if houseboat and that corny little joke helps you to remember the plus c, then I'm all for it. Let's go ahead and do another one. We have root x plus 1 over 2 root x dx, and we want to take the integral of that. Now, we can, of course, split it up. But just like differentiation, anytime you see a radical, the thing that you ought to be thinking, or the thing that you ought to perhaps be doing, is go ahead and put it in terms of a fractional exponent, because all radicals imply fractional exponents. You're going to be using the power rule, the undoing of the power rule, so you might as well go ahead and put it in terms of an exponent, right? So we're going to go ahead and add 1 to that exponent. We're going to get x to the 3/2 over 3/2. I know that that constant, that coefficient 1/2, just kind of comes along for the ride. X to the negative 1/2. Let's add 1 to negative 1/2, and we're going to get positive 1/2 plus c. Now, of course, that right there and that denominator cancel out. And we're going to get, now remember when we divide by 3/2, it's the same as multiplying by 2/3. 2/3 x to the 3/2 plus x to the 1/2 plus c. And that is how we anti-differentiate or integrate that indefinite integral right there. Okay? Well, these are all polynomial of a sort and sort of that family. So let's go ahead and try one that's a little bit, far afield from that. How about we have 2 sine x plus 3 cosine x dx. Okay? Well, like we've done in the past, you can actually break it up into 2 separate integrals, pulling the coefficients out in front because they are constants. From here, we remember that sine has a derivative of cosine, but sine is the derivative of negative cosine. Okay, and that's what you're doing when you're integrating, right? You're taking the antiderivative. You're asking yourself, this thing in the integrand right here, what is it the derivative of? Sine is the derivative of negative cosine, so that becomes negative 2 cosine x. And then cosine has a derivative of negative sine, but cosine is the derivative of sine. So we have plus 3 sine x. But of course, I'm not done until I add my plus c. And that is the integral of this trigonometric integral right here. Okay, let's do another example. Let's do sort of a hybrid integral. How about we have theta squared plus secant squared theta d theta. Now here's the thing. Despite the fact that that's theta, that's really just the same thing as if I had x squared in my integrand, right? And so when I actually split that up, if I choose to do so, and you don't have to, but sometimes right at the beginning when we're just getting used to integration, it actually helps to split it up so that you can actually see it a little bit better. This is just a polynomial. This actually winds up being 1/3 theta cubed. The question is, what is secant squared the derivative of? And secant squared is the derivative of tangent. So this winds up being tangent theta, and then we just tack on a plus c, and we have successfully integrated. Okay, let's do another one. How about we have 2 to the x plus x squared? Now remember, we sort of put these right next to each other. We juxtaposed them when we were doing differentiation because we wanted to underscore the fact that they had different differentiation rules. One is an exponential where the constant is the base and the exponent is the variable, and the other one is exactly the opposite. The base is the exponent and the constant is up there in the exponent. So what we want to do is we want to remember, well, you know that a to the x is equal to, when you take the derivative, a to the x, natural log a, right? So what do you suppose the integral of a to the x is? Well, it would just be a to the x over natural log a plus c. Okay, it's exactly the opposite move. Because here's the thing. Remember, in order to integrate, what you need is you need the integrand to be a recognizable derivative of something. Okay? So really, what you really did is you turned this into this first. Okay? This became this. Now remember, a is a constant, so natural log a is a constant. And all I've done here in changing it from this simple integral right here into this is I've multiplied by natural log a and I've divided by natural log a. That's the multiplicative inverse property. All I've done is multiply by 1 in a strategic and creative way. Now this should be recognizable. It's this. So if integration or antidifferentiation is going back to what's in this bracket right here, I have what I need, okay? And so this integral becomes a to the x, and then I just have to tack on the 1 over natural log a, which is exactly what I have right here. So right here, if I want to go ahead and split this up, and I'm going to go ahead and continue doing this just for a couple more problems, just to make sure that we actually see it well. This becomes 2 to the x over natural log 2 plus x cubed over 3 plus c. And that right there is my integral. Okay? Now, that winds up being easy enough. Let's go ahead and do a few more. And we'll just sort of do just kind of a smattering. How about x squared plus x plus 1 over root x dx? And you're thinking to yourself, oh my gosh, that's a rational expression and the integrand. I have no idea what to do. Okay, this is where we go back to the principle that I introduced last year, which is stop, think, then do. Okay? That being the most important part. Stop, think, then do. Okay? And, you know, this comes into play when we deal with trigonometric integrals and a whole host of other things, because you might need to change the form in order for it to be easier to do, or in fact possible to do at all. Okay? Now, there's something that I know about rational expressions of this variety. Rational expressions of this variety can be broken apart very easily and simplified because I have a monomial denominator. Okay? And therefore what I have here is I have x squared over x to the 1/2 plus x over x to the 1/2 plus 1 over x to the 1/2. And of course I don't usually, I wouldn't usually write this out for you, but just to underscore exactly, how I'm breaking it apart. I'm turning the root x into x to the 1/2, which of course is what it implies, and then I'm just breaking apart the 3 terms in the numerator, each individually over that denominator, and then I get x to the 3/2 plus x to the 1/2 plus x to the negative 1/2 dx. Okay? And because I stopped and I thought about it before I moved on, this winds up being an incredibly easy integration problem to actually do. So I have x to the 5/2 over 5/2, x to the 3/2 over 3/2, and x to the 1/2 over 1/2. Oh gosh, that's an awful 1/2. Sometimes your hand just doesn't do what your mind wants it to do, right? Okay, and so from here we can go ahead and simplify because, officially those are complex fractions. You do have fractions in those big denominators. And so we have 3/2 and then 2x to the 1/2 plus c. And that right there is my integral. Okay. Now, there are several more that I'd like to go ahead and do. So we'll go ahead and do 2 videos on the indefinite integral before we get to the net change theorem, which is, of course, the meat of 5.4. So we'll look for that. I don't know how many we'll do on the net change theorem, but we'll just keep going on those until I feel like we've actually covered sort of all the ins and outs of it. Okay?